Hi, I'm Ryan Nicol, CTO at DSA Ocean, and today we're going to talk about how you can go about sizing fin stabilizer systems at the earliest stages of design. So the point of doing this is that when you're at the early stage conceptual design and things are changing really rapidly, the hull form, the ship particulars, you're really in an exploration phase, you may want to go through a process of evaluating what might be possible with fin stabilizer systems and improving comfort and improving ship performance. And this is where you need to figure out, well, what kind of fin area you want to use and how do you get that into the Proteus DS Shipmo 3D toolset. So, for example, when you look at the generic yacht project, the 50-meter yacht, they don't come with fin stabilizers configured for them, and that's something that you can do relatively quickly. So when you look at the project settings, you'll actually see it does say number of fin stabilizers too. The projects are configured this way so because it's a project level setting. You can see that it shows up in all of the different applications. So what you really need to do in build ship is take a look at the ship appendages, and then when you look at stabilizer fins and edit the fins that are defined here, you'll find that they have, in amongst other parameters here, the span and the chord are basically so small as to be insignificant. They're not going to affect the ship performance at all. So this is where you would want to go, and usually the first question that people come up with is like, well, what's a reasonable fin area to be working with given my ship size? That's kind of what I want to talk about today. There's other effects like, well, where do I put them on the ship, and the details of the control gains and so on. We'll deal with these in other videos in more detail, but suffice to say, the fin area is usually something that you need to get a little bit of a handle on. And the nice thing is there's some resources that available on commercial equipment supplier websites that can give you some idea of what to do. Now, this kind of thing is not meant for the final design. It's just meant for a rough idea to get the ball rolling, to start getting some insight into what's possible with your ship design. So what we're going to do is take a quick look at some definitions here. So here we have a picture of a ship, and then we've got fin stabilizers on here, and the way that we are using this information on span, S, and chord, C here, is illustrated here. So the area is going to be the span times the chord, the aspect ratio is the span divided by the chord. So if you have an idea of what the area is and the aspect ratio is from, say, a commercially available product, you can define the span from these relationship and the chord from these relationships here. So what kind of commercially available parameters are we talking about exactly? Well, when we go on a few well-known equipment suppliers, like for example Quantum, quantumstabilizers.com, and if you go to products and technical specifications, you'll see on their website here, just for example, under the underway S-type fin, let's take a look at QC 1800 here. We'll open that brochure. Some good information here with reference fin areas, and you'll see fin size range. This is what's key here. Typical vessel length, 45 to 60 meters. Again, this is just, it's not a hard and fast rule. There's way more details that are involved, but it's just giving you something in the realm of possibility, right? So, in this realm, maybe we might pick something like, 3-meter area, and then a sort of a typical aspect ratio, 0.4 to 0.5. Okay, this is something to work with, right? Again, for the earliest of stages of design, there's many other reasons to consult down the road with an equipment supplier. There's many other aspects of design beyond just the hydrodynamics, but it's just meant for a starting point. So here we have some details. Another well-known equipment supplier, Naiad Dynamics, so naiad.com. If you go under products on their website and under hydraulic stabilizers, they've got a wide range of series here. And under this brochure, you can see Naiad model series, overall ship reference length. So this is going to be for, like yacht type systems. We see 42 to 55 here, 41 to 52, and a 3-meter area would fit within these realm, the size of systems as well. Another one, CMC Marine, has a wide range of stabilizers under products. So cmcmarine.com under fin stabilizers. You can see their LR system is for displacement or semi-displacement yachts. We scroll down here, you'll see some information, and actually under their company brochure, you'll find some information on suggested sizes here. So for the LR system, overall, length overall, sort of 40 to 50, 40 to 50, greater than 50, you'll see, 3 meter wouldn't be out of the question here for their systems as well. Anyway, there's some guidance there and just some examples. So we'll use this as an example here in a moment. But first off, let's just take a look at what happens when we look at the system. So we might rename this build ship file here. We'll just add a prefix bare hull. We'll run that. Okay, and then when I go to CKeep regular, make sure we load this bare hull ship model file. And in CKeep regular, what we're going to be doing is looking at 0, 12 knots, a couple of different, we really just want to be looking at a beam C scenario. That's the worst case scenario for roll motions. Now, this is not motion in a specific C way, but the roll RAO is going to govern and give an indicator of roll performance. So let's jump to the 12 knot speed and we'll look at 90 degrees beam loading case, and here we have roll RAO of basically 11, so it's quite high. You see quite a peak in the roll response here, so that's when it's resonant in roll at the natural roll period. That's a pretty high response. It's going to correlate to a lot of motion, right? So let's look at what happens when we add some stabilizers. Again, this is not optimized. It's just the earliest of early stage, kind of evaluations. We'll put the QT 1800S in here. We'll go back to the website here. And what I've done is I've just made a little Excel spreadsheet here with the area and the aspect ratio and spitting out those relationships that I was talking about. So say we pick a 3 meter area here, aspect ratio of 0.5. I mean, we could play with this and change the numbers a little bit here, but these are the numbers I want to put in to my build ship project here for that. So go back over here to build ship. We'll edit stabilizer fin. Okay, for our span, we'll put in 1.225, chord 2.45, 2.45. Okay. And we'll just give this, okay, we're giving this build ship project file a different name so I can remember it and differentiate it from another one. So we'll run that. We look at the ship with stabilizer fins. Now I've behind the scenes I've done some other editing here, so I've got the fins, at the maximum beam just to get sort of the best, kind of roll moment, for those fins. One thing I forgot to do. That looks about right for the aspect ratio that we were kind of looking for. So let's go back to build ship here. I forgot to set a control gain. So roll velocity gain. Usually this is the only thing that really you need to do. This is going to make the fins actuate and get an angle of attack, based on how much roll velocity there is in the ship. That's pretty common. We'll expand on setting those control gains at another time in another video, but something in the realm of 1 to 10 is typical. So we'll go back to CKeep regular here. We'll select our QC 1800 build ship file, ship model file, and run the roll RAO. And let's take a look at what this looks like. So at 12 knots and 90 degrees, so instead of an 11 roll RAO, we have 1.6. So it's a huge reduction in peak RAO from those fin stabilizers. You'll notice also that what shows up here is an RAO for the fin stabilizers as well. So this is not the same thing as evaluating the ship motion in a specific sea state, but this is always the first step in evaluating, like, well, what's going on, how effective are the fin stabilizers in the best case scenario, and it's showing there's a huge impact in reducing roll motion. So in any case, the main point was to highlight what could you do with information like this, and where could you find information that might give you some idea at the earliest stages of design when you're rapidly going through lots of changes in a conceptual stage, and then leverage this kind of information to explore what might be possible. Of course, down the road, it makes a lot of sense to collaborate and work with these equipment suppliers, because there's many other considerations about space for equipment, really fine-tuning that hydrodynamic performance and so on. But it's just a starting point. So in the meantime, thanks for watching.